Hi there and welcome to this course on nuclear physics. This is our first video, which is basically going to look at mass defect and binding energy. Now, in order to understand this idea of mass defect and binding energy and the concept of nuclear physics, we have to understand that basically we're dealing with the nucleus of any atom. Now, in the nucleus of any atom, we have particles called nucleons. Now, these nucleons basically come in two forms. We've got the neutron and the proton. So anything which is present inside the nucleus will be called one of those nucleons, okay? So it's a particle of that nucleus. Now, what was observed was that between the mass of a nucleus and its constituent nucleons, we had this scenario, that the mass of the nucleus was always less than the mass of the constituent nucleons. For example, let's look at our nucleus that we've got on the left hand side. We can see here that basically we've got 1, 2, 3, 4, 5, 6 positive charges. Those are the protons. We've also got 1, 2, 3, 4, 5, 6 white neutrons. Basically, this is the atom of the nucleus of carbon. Now, if we were then to look at the mass of the constituent components of the 6 protons on their own and 6 neutrons on their own, what we notice is their mass is actually greater than the mass of the nucleus. Now, the laws basically state that mass must always be conserved. So, what has happened to that missing mass? Where has it gone? Well, where it's actually gone is into what's something known as binding energy. And this links in really well with Einstein's E equals mc squared. Basically what he states is E, energy, is the same as mass. And they can interlink. If you lose mass, you've gained energy somewhere else and vice versa. So mass and energy are combined together. And where this loss of mass has come from is the binding energy, which basically holds the nucleus together. So it literally doesn't have mass, it's got this energy. Now this binding energy is the glue, and we often call it in physics, that strong nuclear force which is holding the nucleus together. Remember, they're all positive charges in the protons. There's no negatives to balance them out. The only thing we've got is these spaces of these neutrons. Now, when we're dealing with large, unstable nuclei, what happens is these positive charges want to break free with each other. There's this repulsive force. Now, the binding energy is the glue which is holding that repulsive force in place. So, basically, a few more terms that we need to know about masses. Often we can deal with them as what's known as atomic mass units, often called just U, and 1 U is 1/12 of the mass of a carbon atom. These values will be given to you in an exam. There's no reason for you to have to go away and learn them, because you can Google them anyway. But 1 U is basically 1.6606 times 10 to the negative 27 kilograms. The reason why we use these atomic mass units is just to simplify our calculations. So basically what we've got is we've got masses of our particles. Protons is 1.007 276 U's. Neutrons are 1.0086665 U's, and an electron is 0.000549 U's. Notice that the electrons there have got a minuscule mass. They still have a mass, and for most of your chemistry and physics learning, we've already said electrons don't have a mass. Well, we do know that they actually do. Now, we can also have this in the form of kilograms. So it doesn't matter which way we work with them, we just need to know that if we're doing everything in use, then we have to convert into kilograms later on. You'll see why in a moment, but it's a nice easy way of using these numbers. So you might be given things in atomic mass units, or you might be given things in kilograms. Just be aware of which one you are, because there is going to have to be a conversion from one to the other. Okay, so let's look at carbon. We know that carbon is made up of 6 protons and 6 neutrons and 6 electrons spinning around the outside. Notice the protons and the neutrons on the nucleus, they're the nucleons holding the nucleus in in together, and around that we've got this binding energy. Now, if we look at the masses, this is where it will become clear, this interrelationship between mass and energy. So what we can do is take the mass of our protons and our neutrons. Now, we've got 6 protons, so obviously we would multiply that by our factor that we had earlier. And if we just look, I'll just go back, whoops, go back one more. So 1U is 1.6606 times 10 to the negative 27 kilograms. So all I've done is multiplied that by 6 to give me the protons, multiplied the mass of neutrons by that value to give me my value in neutrons, and multiplied the mass of electrons by 6 in order to give me the mass of electrons. I hope that makes sense. So we've used those values, sorry, here we go, these values down on the right, the yellow, the green and the magenta colors, and we've multiplied those by 6 in order to work out the total mass of carbon with its constituent parts. So it's 12.098940 units, atomic mass units. Obviously, if I wanted to convert that into kilograms, I'd have to multiply it by that 1.66 times 10 to the negative 27 kilograms. Okay, so that's all well and good. We know that those are the constituent components, but let's have a look. Carbon-12 has a mass of 12.00 atomic mass units. Now this is less, as we can see, than our 12.09894 atomic mass units, which is made up of the individual components. So we've got a mass difference, or a mass deficit, or a mass defect. Okay, that energy or that mass has decreased. We've gone from something really, really big to something really, really small. Now, we can calculate that mass or that energy. Okay, remember I said mass and energy are combined. So we do to get this mass deficit. So if I take the two numbers away, I take 12.098940 and take 12 away from that, I get a mass defect of 0.98940 units. Now, this is the binding energy. This is the energy in the form of lost mass. Okay, so we can now link this with Einstein's equation. Now, Einstein's equation, as we know, is E equals mc squared. Well, instead of m, we're going to look at the mass, or the mass defect, and that really is the change in mass. Hence we've got delta m there. So E is the binding energy in joules. Delta m is the change in mass, or kilograms, or atomic mass units, and c is the speed of light, 3 times 10 to the 8 meters per second. Note that if I'm dealing with mass in the terms of atomic mass units, I'm going to have to use my scale factor of 1.66 times 10 to the negative 27 in order to convert it into energy, because the mass has always got to be in kilograms. So let's make our calculation. So my binding energy will be calculated as E equals change in mass c squared. So it's going to be 0.98940, which is the change in mass. Now I have to multiply this by 1.66 times 10 to the negative 27 to convert it into kilograms. And then I multiply it by the light speed squared. And the binding energy that we get holding the nucleus, or the constituent components of the nucleus, in place is 1.48 times 10 to the negative 10 joules of energy. Now this is what we've got for one atom. Now remember, in the sample we're going to have huge amounts of energy. Now hopefully what I would hope you'd understand is, when we talk about nuclear power or nuclear energy, when we split these particles, we've got this huge amount of energy which is available, and this can be calculated using this change in mass and E equals mc squared calculation. So another thing that we can put it in together is we can express the binding energy in the forms of mega electron volts. Remember that we're talking about electron volts is joules per coulomb, and basically what we've got is one atomic mass unit mass defect is equivalent to 931 mega electron volts. Again, that value will be given to you in an exam, so you don't have to remember the comparison. But one mass defect, or 1 U mass defect, is equivalent to 931 mega electron volts. So as a result, I can convert it into to convert my atomic mass units into a mega electron volts, which would be 92.1 mega electron volts. Now, this is the amount of energy that I would have to actually put in to actually give the constituent 6 protons, 6 neutrons, and 6 electrons their overall mass. So I'd have to put energy in order to give the mass out at the end, so that everything balances. So, to recap, the binding energy of a nucleus is the energy converted from mass when a nucleus is formed from its constituent nuclear particles, all initially in their free state. So we basically take our protons, our neutrons, electrons, combine them together, and what we'll find, that loss of mass will be due to the energy which is holding it in place. Okay, well, I hope that makes a lot of sense to you. Do check out the exemplary video which I've put on, where we've run through a couple of problems, and then I've put together a worksheet that you can actually utilize as well. So I hope that's made sense to you. Thank you for watching, and I look forward to you joining me again. Bye for now.